So in this, first we are going to do the feature extraction from the images, because we had only the image data and we didn't have anything or any data about the features of the leaf, large, small, and how thin is a leaf, or how voluminous is a leaf in 2 dimension, those things. So let's first do the feature extraction stuff, and then we will apply the concept we have learned onto the uh, data set of features of each leaf. So let's start. Step is now feature extraction. Feature extraction. First we will reshape the images we had in our A matrix in the previous videos. That matrix stored images as column vectors, right? So column row vectors. Row vectors. So we'll reshape that first. Reshaping and storing the images in a 3D matrix in rectangular, or for that matter square form. This is a comment. Okay, for that matter, let's loop it for I equals 1 to 9 images. We had 9 images, right? Let's call it leaf images. Leaf images equals these are going to be the reshaped values. Reshape of A, and row is going to represent the image, right? I and all the columns, and it has to be given the shape of X pixel and Y pixel. X pixel number of rows and Y pixel number of columns. PIXEL, yeah, underscore. I think this is right. Yeah, we have to store it in 3 dimension, right? So leaf images is going to have all the rows, all columns, and ith value, or let's say ith stage in the Z direction or the 3D direction is going to represent ith image. So this is how we store it, and initially it doesn't know what leaf images is, but yeah, it can, since we are not using this already here, it can create one, so we don't have to worry about predefining it, I think. Next, we'll talk about a bit about features we are going to deal with are as the following. The first feature is going to be the area, and it's basically the number of pixels in the leaf boundary, right? Number of pixels within the leaf boundary, and this basically helps distinguish between large and small leaves. So helps distinguish between big and small leaves. Second feature is going to be the perimeter. Perimeter. This identifies how jagged or smooth are the edges of the leaf by measuring the outline length, and is, not to surprise, simply the number of boundary pixels on the leaf. Is basically number of boundary pixels of the leaf, and helps to know how jagged or smooth is the leaf boundary. Boundary is nothing but the perimeter. Now, the third property or feature is going to be the compactness. 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 This helps us identify if the leaf is more of a round shape or an elongated shape. Then a circular leaf has a, let's say, lower compactness, lower compactness, while the irregular ones irregular ones have higher compactness. Next, fourth point. Fourth feature is going to be the eccentricity. Eccentricity. This is basically the ratio of major axis to the minor axis of, let's say, the best fitting ellipse. Ratio of major axis to the minor axis of the best fitting ellipse. Ellipse, it has one L or two L. I think let's go for two L's for now. Ellipse over the leaf. And yeah, high eccentricity would mean the major axis is long. That would mean elongated leaf. And low eccentricity means it is more of a rounded kind of leaf, because when major axis tries to approach the minor axis, an ellipse converts to leaf. Sorry, not leaf, a circle. So high eccentricity means a long leaf, while low eccentricity means leaf is about a round shape. Let's say that. Let's put it like that. Next, fifth feature is going to be the aspect ratio. Aeronautical engineers and aerospace engineers would be thrilled by this now, because they deal with aspect ratios of wings and all. So we are dealing with aspect ratios of leaves now. Aspect ratio. Aspect ratio is RATIO. Aspect ratio is if you fit a bounding box to the leaf, it is the ratio of leaves bounding box width to height. Ratio of width to height of the bounding box, right? Yeah. This helps separate broad leaves from thin ones. Leaves from thin ones. So these were the 5 features. Let's go for extracting these kind of features from the leaves we already have. So let's say this is we'll first prepare a list. Okay, we'll prepare a list for the features of the leaves. Preparing a list for the features. Let's call it just features is just a null vector, let's say, or null list. What we'll do now is we'll loop through each leaf image and extract all the features for each leaf and store it in the list. For I equals 1 to 9, for I equals 1 to 9, first what we do is select the corresponding leaf image, right? First we'll select the corresponding leaf image, selecting the, let's say, ith leaf image, leaf, let's call it, it's taken leaf images, because leaf images matrix is a 3D matrix having images along the z direction, right? Different images along z directions. So we'll take an image ith position of z. So now we have taken the image, the leaf. Next what we do is we binarize the image using the threshold, or it will define its own threshold. So we'll binarize the image, binarize the image, that's it. Threshold it will take care of. Yeah, by the way, binarize is see, the images we already have are on a spectrum of grayscale, right? It can take, any pixel can take any value between 0 and 1, that is one side representing white and one side other representing the complete black. But here binarize, this actually puts a threshold, and anything less than that threshold will be given a certain color completely, and anything above that threshold is given the opposite color. So there is no gray image here, a gray pixel here, we only have white or black pixels here. That's what binarize does. Let's call it BW leaf black and white leaf, because after being binarized it's going to be black and white. I am binarize of leaf. Now the leaf is binarized. Next, labeling the connected components. Okay, labeling the connected components. These are basically the features only. Why connected? Because they may have some correlation with each other. So we can call it connected components, or let's say call it labeling the components or features. And how do we do that? We will use the function region props, region props, region props of BW leaf, this leaf, and the parameters or features we want, we are going to mention that. First is area, second was perimeter, third was eccentricity, what happened here? Eccentricity, spelling mistake, ECC eccentricity. Oh, okay, spelling was right, only there was an extra quote. Oh, there was a missing quote. And next is, we can take major axis length and minor axis length also as two other features. Major major, uh, because these are the lengths that we use to calculate the aspect ratio, right? So minor axis length. Yeah, and we are going to store these stats in some structure. um, let's call the variable as stats. Now it's going to store in the stats structure these values. Once we have gotten those values in the stats structure, we extract them from that structure, right? uh, let's say getting the features from region props structure. We'll take out each feature. Let's call the first feature area. This is our name we are giving. So from stats area we get that. Next is perimeter. Perimeter is going to be again taken from stats dot perimeter. uh, Next was major axis, minor axis, eccentricity. So eccentricity was stats dot accent. It was capital E, right? Huh. Eccentricity. Next was uh, major axis. Major axis. Major axis is stats dot major axis length. Major axis length. Next, we take minor axis also, same way. Minor axis is stats dot minor axis length. So this was about extracting the features. But now we know these features. We are going to now calculate the actual features we needed. The compactness, eccentricity and aspect ratio. So going to calculate the compactness. Calculating the compactness. Calculating compactness. Let's call it compactness only. Compactness equals perimeter square divided by area. That's how it's defined. Perimeter square divided by area. Next is next was eccentricity. eccentricity eccentricity is eccentricity we already gave it, right? So we need not calculate eccentricity. Instead what was remaining is compactness is done, aspect ratio is remaining. Calculating aspect ratio. Calculating the aspect ratio. Calculating aspect ratio. Let's call it aspect ratio equals simply major axis by minor axis. major underscore axis divided by minor axis. Next what we do is we iteratively append these features into the features matrix. Let's call it features. Appending and storing the features into the features matrix. matrix features equals features comma uh, see we are going to have all the features along column, each feature along each column. So the leaf wise is going to be row wise. That is, the each leaf represents each row and each column represents each feature. So the iteration is going to be for leaves. So let's that would mean the iteration is going to be the therefore row. Then we have to switch row as the iteration proceeds because each row is for each leaf, right? So next we append area and perimeter and compactness, eccentricity, and finally the aspect ratio. That's what we learned, right? Ratio. So this was about appending the features, and this actually creates the data set. This part creates the data set for our analysis. Feature extraction is done. First, let's see if we are getting the features properly, then we can proceed. We can run this. We don't need figures. We will just check for the unrecognized field name perimeter line 184, line 184. Oh, this should be capital P, right? Nothing else. Okay, seems okay. No error. So let's check the matrix features. Features. Yeah. So these are the features. So this is for the first leaf, all the features, while this is for the first leaf, and this is first leaf's first feature, that was area. This is first leaf second feature, that is perimeter. First leaf third feature, compactness, and the first leaf fourth feature, which is eccentricity, and the first leaf's fifth feature, that is aspect ratio. And this is similarly for the second leaf, third leaf, 4, 5, 6, 7, 8, and finally ninth leaf. So we are done with the data set now. Mm. So far so good. Let's move ahead now. We'll name the features also. We'll label the features also in the matrix. Uh, we can do that as follows. We display this properly, displaying the features matrix, displaying the features matrix, and for that, uh, we create a set of names which are parameters. Let's call parameters or parameter labels, because these are going to be labels. Labels. I think that is the correct spelling. Mm. First parameter is going to be the area, right? The area. Second parameter is going to be the perimeter. Third parameter is compactness. Compactness. That's how we did. First parameter is area, perimeter, compactness. Compactness. Fourth is eccentricity and aspect ratio. Fourth is eccentricity, and fifth is aspect ratio. This aspect ratio. This is our label set. We can do something like follows. We'll just display this once again. Display display again the same thing. We will display this, and then we will display the matrix, features matrix. Let's see how it goes. Don't need to this. Some error. Too many input arguments. Too many input arguments. Oh, these are not to be separated by commas. You can have spaces instead. This should work. Area, perimeter, compactness, eccentricity, aspect ratio. So these are the names and this is the table.